Okay, today what we're going to cover, we're going to start with DMA80 Section 5. And in Section 5, we're going to be looking at rationalizing. Either it'll ask you to rationalize the numerator, or it'll ask you to rationalize the denominator. What we are doing when we rationalize is we are removing the radical from whichever location that we're being asked. When we rationalize a denominator or numerator, either there's going to be one term or there's going to be two terms. The majority of your test questions you will be rationalizing and there will be one term. There will only be one question where you have to rationalize and remove two terms. One thing that I want you to think of is if we have, let's say, the square root of 25x to the fourth power. What that means is I would have a 5 times 5, and I would have a total of 4 x's. When we are rationalizing something, what we're trying to do is to be sure that everything that's under the radical can be removed so there is no longer a radical. The first two examples I'm going to show you here are going to be perfect squares or perfect cubes where everything will come out. Then I'm going to give you an example where we have to determine what more we need to multiply by for it to be able to come out. That in turn we will then apply to the rationalizing problems. So to start with, if we have 25x to the fourth, if I factored, I would have 5 times 5 and the 4 x's. There is not an index written here, but the understood index is a 2. So that means you need pairs. So when I have this pair of 5s, that means a 5 is going to come out. For this pair of, okay, I just had a message that the microphone stopped working for a second. I hope you can now hear me now. Somebody at least speak up and say yes, that they can hear me. Okay, all right, thank you. I just want to make sure because I had that little message that said something with the mic wasn't working properly. Okay, but as long as it's back on now. If I go silent, somebody speak up and let me know, okay? All right, so we have 5x squared. Let's say we have the cubed root of 8x to the third z to the sixth. Okay, so if I have a cubed root, what I have is the 8 would be 2 times 2 is 4, 4 times 2 is 8. I would have 3 x's, and I'm going to have 6 z's. So if I am simplifying this, the index of 3 means that I need 3 of the same for it to come out. So I have a group of 3 2's, that means a 2 comes out. I have a group of 3 x's, that means an x will come out. This is one group of 3 z's. This is another group of 3 z's. So when I simplify this, this is a perfect cubed root. I have a 2, an x, and my z is to the power of 2. So the first thing is I want you to understand, based on what the index is, if I had an index of 5, that means I would need 5 of the same item for it to come out from under the radical. Now, let me give you a scenario. And if we were to rationalize something, let's say I have, and I want to start with a cubed root. Let's say I have the cubed root of 5x squared y to the third z. If I wanted to rationalize this, I would have to figure out what would I multiply by for something to come out from under the radical. So, and I'm going to exaggerate by writing these out completely. I have a 5, I have 2 x's, I have 3 y's, I have 1 z. I just wanted to exaggerate that so we can see what we have here. Here I have 1 5. In order for my 5 to come out from under the radical, I need a total of, and if you look at this index, I need a total of 3. So if I have 1 5, I would need 2 more 5's. If I have 2 more 5's, I then would have a total of 3 5's, so that 5 will come out from under the radical. I have 1, and when we get into rationalizing, we have to figure out how many more we need in order for the 5 to come out. So if I have 1, I need 2 more to have my total of 3. Let's look at the x's. For the x, I have 2 x's. I need 3 for it to come out, so I only need 1 more x here. So if I have 2 x's, this 1x, they now can come out as an x because I have a total of 3 x's. For my y, I have 3 y's. 3 y's means 1 y will come out. I don't need any more because I have exactly an even number of a grouping for 3. For the z, I only have 1 z. I would need 2 more z's to give me a total of 3 z's. Then at that point, my z can come out from under the radical. So when we're doing our problems of rationalizing, we are looking at a denominator we are given. We're going to break it down, and then we're going to determine how many more of each individual number or variable that we might need to have a total to meet the index, and that in turn would allow those to come out from under the radical. Once that radical is removed, we have performed the operation of rationalizing either the numerator or the denominator of that problem. Okay, so if you look in your workbook on page 8-38, we have a problem here where we have 5 over the square root of 3. They are asking us to rationalize the denominator. The numerator is a whole number. There's nothing we can do to reduce or simplify it. What we have to do is we're going to multiply top and bottom because we're going to need to rationalize the denominator as the square root of 3. If I have 1 3, I need a total of, because the index is understood to be a 2, that means I need 2 3's. So it only takes 1 more to give me a pair of 3's. So now that 3 in essence would come out from under the radical. Now, you can multiply any fraction or rational expression by a 1. So that fraction part here, that's why I drew the big yellow 1 around it, in essence is a whole number 1. As long as your numerator and denominator are the same, square root 3 over square root 3 is 1. So in my answer, I now have to combine what I have in the top, which is a 5 square root 3. Nothing here can simplify. The 3's under the radical, that's a whole number 3, and the fraction 5 over 3 itself does not reduce any further. And that's it. We have rationalized the denominator. Let's look at number 6 on that same page. Number 6, we have a whole number 2 square root 9 over the square root of 20y. Now, what I always recommend is if anything can be simplified, let's simplify first. When I look at the square root of 9, what is the square root of 9? It is a 3. So that means I have 2 times 3. Or 2 times 3 would give me, in essence, the number 6. Square root of 9 is 3. 2 times 3 is 6. For the square root of 20y, let's go to our calculator and remember what we did last week. We're going to do 20 divided by x squared. You'll always use the index for the exponent. Second table, a 1 would be here, but there's not one. So my first pair of whole numbers is 2, 5. So that means a 2 comes out. Under the radical would be a 5, and we still have that single y. So this would be 2 square root 5y. I like to simplify first because if you don't simplify first, you end up having very large values that you have a lot of reducing to do. So my whole number 2 is on the outside. I have 1 5 is a square root. I need another 5. When I have that pair of 5s, the 5 comes out. I have 1 y. I need a second y. Once I have a pair of y's, that y comes out. This number in front is a whole number. Let me just make note that it's a whole number. And 5 times 2 would give me 10y. 5 times 2 is 10, and the y had already come out. What goes here is the same thing we had under the radical, the 5 and the y. This is just 6 square root 5y. So when you rationalize, you will be pulling out the radical from the denominator, but then it would appear in the top, and that's absolutely okay. They're just telling us which location they do not want or they want the radical removed from. Now, this is one problem that we can simplify a little bit further. 6 and 10 are both even. 2 goes into 6 3 times, and 2 goes into 10 5 times. So my final answer would be 3 square root 5y over 5y. This is under a radical. This is not. That cannot be reduced in any way. Okay, now let's do an example where we have a cubed root. We're going to rationalize with a cubed root. I have the cubed root of m over the cubed root of 27n to the. Okay, in the numerator, we cannot reduce or simplify, factor any further the cube root of m. But in the bottom, 27 would be 3 times 3 is 9, 9 times 3 is 27, and we have a total of 4 n's. So if I'm simplifying this in any way, what I can reduce is I should see that I have a group of 3, so a 3 is going to come out. I have a group of 3 n's, so an n is going to come out. A 3 came out, an n came out, but under the radical, I still have that single n, that single one here, because a group of 3 brought one out, this one still remains. When we multiply, we're going to multiply by the cubed root of something so that we can remove, all we've got to remove is that extra n. If I have 1 n, but I need 3, I'm going to have 2 more n's. Now that I have 3 n's, that n can come out. So if there are 2 n's here, that is an n squared. N squared is not enough to come out from under the radical. So the bottom, we have a 3. We have this n. We have the second n, so that's 3n squared. Under the radical, it's a cubed root. There is 1m, and then there is the n to the second power. Numerator stays just like it is. We cannot do any more simplifying. So you're going to still keep doing this process, whether they say rationalize the numerator or rationalize the denominator. It's going to be the same either way. Now, let me show you what to do if you are rationalizing with 2 terms. I'll start with a simple one, and then I'm going to give you one that I know is like what you're going to have on the test. So starting with this simpler one, we have 6 over 4 minus the square root of 3. When you have two terms, you are going to multiply by the conjugate. The conjugate is going to be the same values as in the denominator, but you are going to switch the sign, switch the middle sign. If it's a plus, you make it minus. If it's a minus, you make it a plus. So for this one, I'm going to multiply by the conjugate, and let me show you what that's going to be. We've got 4 and the square root of 3. Do you see how this one is subtraction? These are both going to become addition. Okay, so that's really what we're going to do. In the numerator, we are going to distribute the 6 times the 4 and the 6 times the square root 3. 6 times 4 is 24. And then we have a plus, and then it's just going to be 6 square root 3. In the denominator here, we are going to need to FOIL this. First, outside, inside, last. My first is 4 times 4, which gives us 16. My outside is the 4 times the positive square root 3. So that's going to be plus 4 square root 3. My inside is going to be, with that being minus, a minus 4 square root 3. My last, we have a negative and a positive. That's going to give us a negative. Notice they are both square root 3, square root 3. There's a pair of 3's. So the 3 is going to come out. Originally, it would be a square root 9, but it comes out as a 3. I personally just write the 3. I don't write the square root of 9. As we look here, and we're simplifying, these two terms cancel out, and 16 minus 3 is going to give us 13. So my denominator here is going to be 13. And we're finished on that one. That's all that you can do there. Give me 1 second to switch to the section 5 here, and let me find one that's going to be like what you'll have on the test, where you have two terms. The ones with two terms are not difficult to do at all. I just like to use the word tedious, because what's going to happen is you have to FOIL the numerator and FOIL the denominator to do this. So let me find an example of one of those that has both two terms on top and bottom. That's a single term. Okay, here we go. We have an 11 with a 3 on both top and bottom, minus and then a plus. Okay, so that's how the original problem was written. I like to, since it's two terms, go ahead and put a parenthesis around both sides. Then what we're going to do is we're going to multiply by the conjugate. The conjugate is going to be both the square roots of 11 and 3. You look at the denominator was a subtraction. So the conjugate is going to be is an addition. So the opposite of the addition, we're going to use subtraction for the conjugate. The top and bottom have to be identical. We're going to put our final answer here in a moment. But what we have to do to solve this is we're going to FOIL the numerator and the denominator. So first, if I FOIL the numerator, if I have square root 11 times square root 11, isn't that the same? So that means for the first term, and 11 is going to come out. Then here I have a positive and a negative, so that's a minus. The 3 times 11 is 33. Here in the middle, I have another, for the inside, I have another minus square root 33. And then my last term, negative times negative is positive. I have a pair of 3's, so that means a 3 comes out. Now I want to combine like terms. So 11 plus 3 gives us 14. This would, in essence, be, and you don't see the number here, but there's an understood 1 here and here. So when we combine these two, that's negative 1 minus 1, that's minus 2 square root 33. So my new numerator is 14 minus 2 square root 33. That's where I FOILed the numerator. Let's now FOIL numerator. Now we're going to FOIL denominator. On the denominator, to start out here, we have a pair of 11s, so an 11 comes out. When we do the outside, we have a minus square root 33. When we do the inside, it becomes a positive square root 33. And when we do the last term, we have a minus and a 3. 11 minus 3 is 8. These two terms, when they get combined, it's a negative 1 plus 1, so they cancel, and all I have for the denominator is an 8. I can do one more thing here. I can now simplify. When I simplify, all three numbers have to have a common factor, and they can all be reduced by 2. So I'm going to put simplify by 2. The 14 would become a 7. The 2 would cancel out as a 1, and we would just have square root 33. The denominator of 8 divided by 2 would give us a 4. And then this would be your final solution. That is the most complicated any of these get. And it's not hard. You just have to tediously keep up with the steps of seeing if something comes out from under the radical, or do you multiply it through, canceling out like terms or combining terms, paying attention to all those signs when you're doing your foiling. Okay, so that is your section 5. And now let's look at section 6. In section 6, we are going to have equations. So we are going to solve the equations that we have. Solving the equations is not terribly difficult. With solving equations, what we have to do is get a radical on one side and then progress our problem from there. So let me give you an example here. Let's say we have 3x minus 2 plus 19 equals 24. I'm going to make note here, get radical alone on the left of equals. In order to get the radical by itself, we're going to subtract 19 to move it to the other side. So the 19 is going to move. Then we have that 3x minus 2 under the radical, and 24 minus 19 is going to give us 5. We're going to take a break for a second and let's just stop and look at this. What we want to do here is to remove the radical. Once the radical is alone, we'll put once alone. To remove radical, you are going to multiply both sides by the index. If it was a cubed root, we'd raise it to the third. If that had been a seventh root, we would raise both sides to the seventh. This one, our index is the understood 2. So if I raise it to the second power, that cancels out and the radical will go away because there's 2 of these, so that whole thing comes out. The right-hand side of the equation, you're also going to raise to that same power as the index. So now magically, the 3x minus 2 is from under the radical. 5 squared, 5 times 5 gives me 25. And from here, I'm just going to make note, you just solve for x. It's just like a dma080 problem, basic algebra. Let's move our 2 to the other side. And we have 3x equals 27. Then we're going to divide both sides by 3, and x is equal to 9. Okay, let's do another one. On this one, let's do one where we have a cubed root. We have the cubed root of 2x minus 3. Then we have a minus 2 equals 5. So my first step is we want to get the radical by itself. So we're going to move this 2 that's all alone over here. So now we have the cubed root of 2x minus 3. 5 plus 2 gives me 7. I'm going to raise it to the power that's the index. So this index is 3, so I'm going to raise both sides to the third power. Now the 2x minus 3 just comes out. I'm going to go to my calculator, and I'm now going to do 7 raised to the third power, 343. To finish solving, I'm just going to solve for x, so let's move that 3 over. 2x equals 346. We're going to divide both sides by 2. So 346 divided by 2 gives us 173. That's really all that you're doing on these. Now there is one, and I even think there's one of these maybe even on the test. Here I've got 2y plus 3 equals negative 4. And there's a note they give you that says work smart, not hard. For this particular problem, there's no need to raise anything to a power or do anything. What they're wanting you to do is to recognize that a square root cannot have a negative answer. That's the whole concept that they're going for here, is that you recognize that there is not going to be a negative answer. So for this one, we would just give no solution. If I had the square root of 16, it's not going to be a negative 4. It's just going to be 4. So in this problem, there's no work to do. You just have to remember that concept. If it had been a cubed root, then yes, you would go about solving it. But since it's a square root, or if it had an even index, you cannot do any more. The other part of section 6 is there are going to be a few problems that you're going to have that are going to be word problems. You will revisit the Pythagorean theorem. You're never going to get away from that. You learned it in DMA 10, and you've seen the Pythagorean theorem throughout all of the DMAs. I'm going to go to the computer for the homework section and pull a couple of problems from there for the word problems. So give me 1 second to pull up that. I would rather give you sample problems like what I know you're going to have. They give very few in the workbook. And I like to kind of go over some that I know you're going to be seeing again. Okay, this is one like I know you will have on the test. A wire is needed to support a vertical pole 19 feet high. A cable will be anchored to a stake 10 feet from the base of the pole. How much cable is needed? So we have 19, we have 10. This is 19, this is 10, this is the 90-degree angle, and we're solving for the hypotenuse. So this is where we're going to use the Pythagorean theorem with the a squared plus b squared equals c squared. As you look at this illustration here, the two sides that form the 90 degrees are your A and B. The diagonal, the C, is your hypotenuse. So we're going to have 19 squared plus 10 squared equals x squared. Okay? I recommend using your calculator. So we're going to do 19 squared plus 10 squared. That's going to give us 461. So 461 is equal to x squared. To get the solution for x, we're going to take the square root of both sides. So for problems like this, let me look back at here. It's going to ask us first for the exact length. Type an exact answer using radicals as needed. Sometimes it'll ask for exact and then an approximate rounded to so many decimal places. So if I were to use my calculator and if I did square root of 461, I would get a decimal answer, the 21.4709. Let's put down here 21.4709. That would be the approximate answer, and they would tell you how far to round if they asked for that. But if they want an exact answer, we know how to do this. We're going to come back to y equals. We're going to type in clear. We're going to do 461 divided by x squared. Second table, we're going to look in the second column and we're going to need to scroll down to see if there is a 1 because we first want to see if it's a perfect square root. Okay, so a 1 should be here. There is not a 1. So we're going to have to scroll back up and we're looking to see for the first pair of whole numbers. So as we go up, I still don't have a whole number in the right column. I'm looking for my first whole number in the right column. Okay, the first whole number I see is the 461. So this one does not reduce any further, so the exact answer is the square root of 461. But if it had been like 2 square root 63, then you would do what comes out and what stays under the radical from the left and the right column. Let's do another word problem. Let me find another one that's going to be similar that you'll have. Okay, this is one I know that's on the test. The formula is S equals 2 square root I minus 9. S equals 2 square root I minus 9. Let me just double check, make sure I wrote it correctly. Okay. In psychology, it's been suggested that the number S of nonsense syllables that a person can repeat consecutively depends on his or her IQ score, I, according to this equation. Use this relationship to estimate the IQ of a person who can repeat 12 nonsense syllables consecutively. Round to the nearest integer as needed. So they're saying round to the nearest whole number when they say integer. So we're plugging in 12 for the letter S. So where the S is, we're going to substitute 12 to square root I minus 9. In your mind, I want you to look at this. That's what we're solving for. So think of it as being just a great big old X. If that had been a big old X there, what we would do is we're going to move the 9 to the other side of the equation. That'll make it cancel out here. And then 12 plus 9 gives us 21 equals 2 square root I. If we're trying to get the I alone, my next step would be to divide both sides by 2. The 2's are going to cancel. 21 divided by 2 is 10.5 equals the square root of I. Now, what did we just mention a moment ago in section 5? That if we want to solve this, the index is a 2, so I would raise it to the second power. That's going to make the I come out from under the radical. If you square one side, you got to square both sides. So we're going to use our calculator, and we're going to do 10.5. We're going to square it, and we get 110.25. 110.25. But they say round to nearest integer. You have to remember, integer means whole number. So if you're rounding to the nearest whole number and you look at the 2, that's going to round to be 110. And that would be your solution. So for any other problems you have in section 6, you're solving for a variable. They may give you some values to plug in, but you're just going to have some radicals in the midst of those particular equations.